This is the 19th lecture in the FOA series on fiber optics. This lecture will discuss OTDR measurement uncertainty. OTDRs are highly useful instruments for testing fiber optics. They're convenient because they work from only one end of the cable, and they create a snapshot of the cable plant at a point in time. That snapshot can be used for immediate analysis of the cable or saved for later use in restoration. However, OTDR measurements are not without their errors or their quirkiness. So let's look at some of those and see how we need to understand them in order to interpret the data. The first problem with OTDRs is their measurement method. OTDRs measure the backscatter from the fiber to infer the loss, not a direct measurement like insertion loss, and this can cause errors in loss measurements. The distance that the OTDR measures depends on the index of refraction of the fiber and the amount of loose fiber in the cable. The OTDR has limited resolution, which may cause some events to be completely missed because they're covered up in the resolution. OTDRs have problems with modal distribution in multi-mode cable. And sometimes OTDRs show ghosts, things that aren't there. Finally, how do you calibrate it? Let's look at each of these in turn. The first sign that most OTDR users have that something is amiss is when they see a gainer on an OTDR trace. The gainer is not unusual. It happens all the time. But we know there's not a, quote, amplifier in the fiber link. So what causes a gainer? Gainers are the first indication for most users that something is strange about OTDR measurements. In fact, the OTDR is measuring the backscattered light. So if we take a fiber and break it and splice it back together so that the backscatter coefficient is the same on both sides, we'll measure the actual loss of that splice. But if we go from a high backscatter fiber to a low backscatter fiber, we will have two things happening: a loss across the splice plus a decrease in signal level because of the lower backscatter. So the measured loss in the OTDR is the actual loss of the splice plus the lower signal level of the backscatter. So the measured loss will be higher than the actual loss. If we reverse that and go from a low backscatter fiber to a high backscatter fiber, we'll have an increase in the backscatter level, an increase in the signal back to the OTDR. So what happens is, if we have a low splice loss and a large change in the backscatter, we will see the loss overcome by the increase in signal level from the higher backscatter, and we'll see a gainer. What people have to understand is that the OTDR is always looking at backscatter, and any change in backscatter affects its measurement. If you need to know the exact loss of a splice between two different fibers, you really have to make the measurement from both directions and average it to remove the difference in the backscatter signal. The OTDR calculates distance from knowing the index of refraction, or NVP, nominal velocity of propagation, of light in the fiber, and the time that it sees to an event. But it turns out that the NVP, or the index of refraction, can vary from fiber to fiber. So there'll always be some error if we don't know the exact NVP, or if we're looking at the average NVP over a large concatenated series of fibers in a cable plant. There's another error in distance measurements, and that is that the fiber is generally longer than the cable. In loose tube cables, there's typically about 1 to 2% more fiber than there is cable in length. In ribbon cable, it's closer to being the same, but there's still a small amount of excess fiber. If you're trying to calibrate this, you can take a reel of cable and you can look at the marked distance on the cable and compare that to the reading on the OTDR and make the correction. But again, if you're looking at a long concatenated cable plant with numerous spliced together sections, you really have to just average it out. And the best rule of thumb is to remember that 1 to 2% is about the amount of excess fiber. That means that if you measure 10 kilometers, that the actual length is going to be less 2%. So if you're trying to find a break in a fiber, you always look before the distance that the OTDR tells you, because that's where the actual cable length will be. The OTDR can completely miss some events if they're close together. Because the OTDR pulse width is variable, that distance can change. But if you have two events that are close together and a wide pulse width, they will be completely lost. Thus, you have to be careful to always try to use the shortest possible pulse to get the best possible resolution. OTDRs have other errors associated with measuring multimode fibers. The outgoing laser test signal is much smaller than the core, so it tends to underestimate loss, and the backscatter signal is probably fully filled, although this is not well understood. So what you see is an average of the outgoing and the return signal. The OTDR, and particularly with multimode fibers, is no substitute for a properly done insertion loss test that controls the mode power distribution from the test source. Sometimes OTDR traces are unreadable. Here's two examples of the same cable, but with very highly reflective events and less reflective. And as you can see, if you get a very highly reflective event that saturates the receiver of the OTDR, you may have a baseline recovery problem that makes it impossible for you to actually make any loss measurements on that cable. Highly reflective events cause another problem in OTDR traces. They're called ghosts. If the light is highly reflective, it can bounce back and forth between connectors and create a secondary reflectance peak at exactly twice the distance from the first peak. If you see a suspicious peak that looks twice as long or twice as far away, then check the distances. If it is exactly double, you know you have a problem. But obviously, it also helps to know the length of the cable you're testing, because then the ghost becomes obvious much more easily. We often get questions about OTDR calibration. Well, OTDR calibration is a complex issue. The time base is calibrated for distance measurements, but the actual distance measurement is going to be influenced by the fiber NVP, or index of refraction. So it's not a big issue. The power linearity is important for measuring loss, but the backscatter coefficient is not a constant, so loss cannot be really calibrated, only linearity. Due to the complexity of calibrating OTDRs, very few are ever calibrated, and we actually don't know any labs that do it routinely. Be sure to see the other FOA lectures on fiber optics. There's 2 others on OTDR testing and others on insertion loss and optical power testing, as well as lectures on designing and installing networks and the spectrum of fiber optic components. Also, refer to the FOA online reference guide on the FOA website for more detailed information on all these topics. We're the Fiber Optic Association, the Professional Society of Fiber Optics. We hope you enjoy this lecture series on fiber optics on YouTube.